Is there anything we're like super worried about?
Yes, for me, it's just like certain cytokines that like which ones are used for like going between like a dendritic cell to CD4 T cell,
Hmm.
like a CD4 T cell to like B cell. Like I think
Okay.
there's a couple differences there.
Yeah.
So it's just those. So
Okay. Cool. Anything else? How are we feeling on transplant stuff? Decent. How about the threshold model? Do we understand that? And selection? Okay. Okay, cool. So let's start with some differentiation stuff then. Oh, how do we feel about VDJ? I know that was a long time ago. I feel like we had some pretty good understanding of it, but we can go over some like practice questions if we have extra time. Okay. Well, let's start then with uh, some of our selection stuff in our T cell differentiation. Yeah, we'll start there. Um, so I just went through the slides and picked out slides that I think are important, and we're just going to go over those again and make sure that we understand them. So stop me at any time if you have questions or if you want me to go over anything in more detail. But this is just a literal review. We're just going to talk about things that we haven't talked about in a while and make sure that we're all following everything. Okay, so in terms of our TH subtypes, we're going to have the main four, which you guys know about because we did them on the maps. Um, I think somewhere a lot of people tend to get confused is what exactly the nuances are between, say, like a TH1, a TH2, and a TH17 in terms of like size of pathogens. Because it's not exactly as simple as like TH1 is virus and TH17 is bacteria. There's some overlap there. So I think this slide highlights really well. We have intracellular pathogens that can be bacterial and can be viral, and those are going to be well targeted by our TH1. The point of TH1 is to phagocytose and induce apoptosis, essentially, because we want to eliminate cells that are infected and have pathogens within them, and we want to phagocytose like the small pathogen pieces, which is most of what we're going to see when we have viruses or intracellular bacteria or small colony bacteria. That's why we have some coexistence between TH1 and TH17 because TH17 also is for bacteria. But the thing about bacteria is a lot of the time, if you have um, like individual bacteria that are small enough, they can eventually collect and become like a colony. And that's when we want that TH17, which introduces some degranulation. So for the most part, we want our TH1 for our like small phagocytosis based our small pathogens that we're going to fight using our small pathogen techniques. And then for our TH2, we want our large pathogens that we're going to use our degranulation and our like large pathogen techniques. And then TH17 is like a little helper for TH1 when we want a little bit of degranulation. Um, so that's the theory behind it. And I think we're pretty solid on that. Um, here's some of that like inter inhibition, how we can see TH1 and TH17 together. We cannot see TH17 and TH2 together because that's too much degranulation and it causes damage to the body. And yes, we can't see TH1 and TH2 together because that's like everything. And that would be stupid to do every single strategy against a pathogen that you're only really going to need to use. Um, like, you want to limit the amount of damage you're doing to the pathogen if it's going to cause too much collateral damage. So that's why we have those inhibitions and also collaborations between these TH types. And that's just more of that. Um, hold on. Let me find the slide that I want. Come on, man. Okay, this one. I love this slide. I really recommend like looking at this slide a lot if you're uncomfortable at all with the cytokines that cause each TH response and that each TH response like results in. Because we have our at the top there, we have the cytokines that result in that class differentiate or that differentiation of that TH cell. And then beneath that, those are the cytokines that that TH cell will now produce. It's like super helpful in distinguishing the before and after and like where these cytokines come from. So if we want to know like what is the signal 3 coming from a dendritic cell that is going to induce that differentiation, it's going to be at the top. In terms of other cytokines that we're going to see from the innate, I recommend, and it sucks and it's like a lot of information, but I really recommend looking again at your innate map like chart thing, the general idea behind some of these patterns that we're going to see in terms of which cytokines relate to which type of pathogen and which cells are going to be producing those cytokines. So I wouldn't stress too much about memorizing all of that. I would recommend looking at it if you want a better idea of exactly what cytokines are going to come from where. For example, IFN gamma, or no, it's IFN alpha and beta, I believe. Don't quote me on that, which are secreted by any nucleated cell, and that's something worth noting. Those are the kind of things that, like, either exceptions or patterns are worth memorizing. I wouldn't get too bogged down in the details of like every single cell and what it's. But yes, if you want to have an understanding of TH cells, this slide, excellent. Okay. That's kind of most of what I want to cover in terms of reviewing our TH differentiation because I feel like generally we have a pretty good grasp on that. Does anybody have any yes?
So the top of that shows like what secreted to that cell differentiate. And it says like signal C study with B cells as well.
Yes. So any like phagocyte is going to have the ability or anything that has PRRs essentially is going to be able to well, not anything that has PRRs, anything that is an immune cell that can secrete things and has PRRs is going to be able to detect the specific patterns of PAMPs that will induce the secretion of these. And like I said, the innate map chart is your best resource for like seeing exactly which cells are going to secrete those things. Which it doesn't reference B cells, but because we need that signal 3, it's pretty safe to assume that that's going to come from our B cell. Okay, any other questions about TH differentiation? Do we want any specific practice with any of the concepts behind it? Do we want to review any? All good on this? Cool. Okay, how do we feel about reading cytokine graphs? Okay, let's go over that. This is one of my favorite topics because it's like pretty straightforward. And once you get the pattern and understand how to read them and how to get your answer, it's like pretty consistently an easy way to get points, basically. So when we see these questions, our first step is deciding if it's TH1 or TH2, because primarily it's going to be one of those. It's going to be TH1 or TH2, which means that we're going to start by isolating our relevant cytokines to TH1 and TH2, which is going to be our IL-12, our IFN gamma, and our IL-4. So for our first step, we're just going to look at those three. IL-4, IL-12, IFN gamma. The reason we're just looking at those three is because IL-12 and IFN gamma are both needed to differentiate into a Th1 cell, and IL-4 is what is needed to differentiate into a Th2 cell. So we start out looking at those three. We have to consider Th1 cells as working like a I think it helps to think of it as a chemical reaction. So you have to have enough of both you have to have both present in order to have the product of a Th1 cell, which means we want to look for our limiting reagent in these. So whichever of these two, IL-12 and IFN gamma, that you have less of, that's your limiting reagent. You can't make this amount of Th1 because you only have this much IFN gamma. When you are taking your exam, I recommend like marking on the graphs where these are. So if I could mark this, I would draw a line across my IFN gamma, and across my IL-12 to mark that that's where my Th1 stops. Then we're going to compare that to our IL-4. And if our IL-4 is higher than that lower level, than that line we just drew, then we know that we have a Th2, which is what we have in the theory. Th2, because our IL-4 is higher than both IFN gamma and IL-12. So once we've done that, we've crossed out our first step. We have a Th2. That informs us of what we could have next. So because of our inability to have, I'm not gonna find that slide. Because of our inability to have Th2 and Th17 at the same time, because that's too much degranulation, we're gonna stop at Th2 and we're gonna just look at Treg. Because Treg can coexist with Th2. So for Treg, we're just gonna look at our our TGF-beta. Again, oops, wrong way. TGF-beta is what causes that differentiation into a Treg cell. So then when we're looking at our cytokine graphs, we want to look at our TGF-beta to figure out Treg. So we know we have Treg because we have a TGF-beta that is above baseline. Does that make sense? Y'all feel confident about this? Okay. Okay, before I move on to the next example, let's say IL-12 and IFN gamma were higher than IL-4. And remember, both of them have to be higher than IL-4 for it to be a Th1 response. If both of them are higher than our IL-4s, we get Th1, and then we know that we can have a Th17 response as well. However, it is important to note that TGF-beta is part of both Treg and Th17, which means they have to share the pool of TGF-beta. So, I'll move to the side. For our TGF-beta, to consider where it's all going, we want to consider that limiting reactant situation again for our Th17. Th17 needs IL-1, it needs IL-6, and it needs TGF-beta, which means that we stop at our lowest, we draw our line across, and then that is how much Th17 we can make. You stop there. You can't make more than that because you need all three in order to differentiate into a Th17. So, whatever TGF-beta is above that, that can go to our Tregs. And then if we're ranking them, we want to compare, like, basically, I think what makes it easiest is if your limiting reactant line is above halfway, we have more Th17. If it's below halfway, we have more Treg. That's how I would represent that. Hopefully you all follow that, and we're going to practice. Okay, we've got 3 examples here. Just take a second, look at them. We'll just start with patient 1 and yeah, break it down. Okay, how are we feeling? Do we have like a pretty good idea? Does anybody want to come like draw how they went through this, or do we just want to go through it? I'll just go through it. Okay, so first, we are looking at TH1 or TH2. So that means we're gonna just look at our IL-4, our IL-12, and our IFN gamma. Brilliant. Between our IL-12 and our IFN gamma, we want to pick whichever one is lower and draw a line across. That is our cap for our IL-1. Cool. However, it is still higher than our IL-4. So we know we have a TH1 response. Brilliant. Did everybody get that? Sick. Okay. Now we don't care about these anymore. They're out of our brain. We only care about our IL-1, our IL-6, and our TGF-beta for the next part. Because now we care about Th17 versus Treg. If we had if we had Th2, would we care about this? Cool. Okay. IL-1, IL-6, and TGF-beta. Our lowest one is our IL-1. So we're gonna mark where that is. And that is our cap for Th17. Cool. This one's kind of a weird example because, as far as I can tell, that's about at the same level that a no response would be. I don't think it's likely that she asks you something like this on the exam, because that would be kind of tricky, not super nice. I don't think that we would have any Th17 based on that comparison to the control. So we're going to assume that there's no Th17 here. Either way, our TGF-beta, our level at which our cap is set, is way below halfway, which means we have more Treg than we have Th17. Which means that when we rank what we have Th1 first, and then we have Treg, and then hypothetically, possibly, we have Th17, but we're going to say no because it's so close to that baseline. Okay, do we feel good about that? Do we want to go through another example? Yes. Oh, yeah, that's a great question. Okay, so earliest response to more progressed response is what our IL-2 tells us. So if we this one's more a comparison between patients because there's not really anything necessarily that we need to compare the IL-2 to directly. So, which of these patients has the most IL-2? Our third patient. What does IL-2 tell us about a response? Proliferation. So we were talking earlier today about our expansion phase of an immune response. IL-2 is like a pretty good marker of our expansion phase. Patient number 2 there, no IL-2, which means they're early in their response, that they haven't made it to that expansion phase yet. We're not doing any proliferation. Patient 1 has more IL-2, so we're gonna assume they're further in their response than patient number 2 is, because they are proliferating, because they have activated T helper cells which are secreting that proliferating cytokine. Patient 3, we can say they've got a lot of IL-2 and they've got a lot of other cytokines going on there. They also have a pretty fair amount of TGF-beta, which means they've got a lot of Treg, which means they're probably far enough in their response to have like damage happening that we need a Treg for. So there we can say patient 2 is earliest in their response, patient 3 is most progressed. Does that make sense? Okay. That's really all that IL-2 tells us in this case, because IL-2 is universal throughout response types. We're going to see it in Th1, Th2, Th17, and also Treg, although that would be like weirder because usually Treg comes with contraction. But I wouldn't focus too much on expansion versus contraction as long as you understand the general premise, which is expansion is that proliferation phase and contraction is once we're pretty much done, we're going to start like packing it up. Cool? Okay. Do we want to practice? No, we're pretty good about that. Okay. I'm gonna go back to my little topic section and we're gonna see, where is this? Here? Yeah. Is there anything else that we want to focus on really strongly before I just start doing like general review stuff? Yes.
Like CD8. So
Yeah. Um, that's a good one because it's weird. Okay, never mind. I don't have any slides on that, so we're gonna just talk about that one. Okay, so CD8 T cells have to be activated once we already have a T helper cell. Um, this is because they have extra signal to an extra signal 2 and an extra signal 3 that they need from a T helper cell. So when we're considering the differences between activations of B cells and CD8 T cells versus the activation of a CD4 T cell, the CD4 T cell just has the signal 1, signal 2, and signal 3, and it gets those from whatever PAPC presented it the epitope on its MHC2. This is the stuff that we talked about a lot before exam 1. For CD8 T cells, they also have that presentation, and this is from a dendritic cell. So the reason that dendritic cells are going to be presenting to CD8 T cells is because they have the ability to cross-present. So we care about dendritic cells because of their ability to do epitope presentation on MHC2 and MHC1. Any nucleic cell has MHC2, MHC1, which means hypothetically anything that can present on MHC2 can also present on MHC1. The difference is that a dendritic cell has the ability to present on MHC1 whatever it has processed through phagocytosis. Does that make sense? The idea that if what we're presenting on MHC2, generally the goal is to have it all be relevant to whatever our initial phagocytosis was that triggered our PRRs. We want whatever we're presenting on our MHC2 to be the same or from the same source as whatever we're presenting on our MHC1, because that's the only way that we can guarantee that we are activating for the same thing. Does that make sense? Okay. So our dendritic cell can do cross-presentation, which means its MHC1 and MHC2 are presenting the same, not the exact same epitopes, but epitopes from the same source. So they are going to be responsible for activating our CD8 T cells. They will provide signal 1, which is MHC1 and CD8 T cells interfacing. Let me write this out. I don't have an eraser. Okay. So we've got our dendritic cells, signal 1, which is MHC1 plus our CD8 TCR. So we still have a TCR, and most of the TCR complex is the same. We just have a CD8 instead of a CD4. And then that's why it interfaces with that MHC1. That's our signal 1 from the dendritic cell to our CD8 T cell. Then we've got our signal 2, which is the same as it is for a for CD4 T cell. So it's our B7 to our CD28. And then we've got our signal 3, which is our cytokines. Here I don't think she's gonna ask you anything about this specifically. because CD8 T cells are designed for apoptosis, that means they are relevant to a viral response primarily, or a Th1 response, because they're only going to want to get involved if you need to be inducing apoptosis. So if you wanted to get specific about what signal 3 might be here, I would assume it's going to look pretty similar to your Th1 cytokines. So we'll call it IFN, gamma, and IL-2. I'm not 100% certain on that, which is probably a good sign that it's not super important in terms of like memorizing for the exam. For our other signal 2 and our other signal 3, those are going to come from our T helper. And we're going to assume this is a Th1. No signal 1 there because our signal 1 comes from this. The reason that our signal 1 is like unique, or the reason that we only have one signal 1 is because that is the whole deciding factor on why this CD8 T cell is special. The variable region on that CD8 T cell is what is making it get activated right now. So that's why we care that we only have one signal 1. Because this is the most important thing in terms of deciding why this specific CD8 T cell is getting activated. For signal 2, we have our CD40 ligand, CD40L, and our CD40. CD40 is on the CD8 T cell. CD40 ligand is on our freshly activated Th1. And then our signal 3 is going to be whatever cytokines. Why do I keep doing this to myself? I'm never going to find this slide. It's going to be whichever exact cytokines are secreted by our Th1 cell, and it's going to be IL-2. You don't even necessarily need to consider IL-2 exactly a signal 2 or signal 3. It's not necessarily like part of the activation process, but it is going to be part of the activation because that's what induces that proliferation. You're also going to get your IL-15 and IL-7. Again, I would say if you don't necessarily have to consider those part of your signal 3, but they will be there because they are for proliferation and memory. Okay. That's like the memorization aspect of things. We can diagram it if you guys are interested in seeing it visually. Otherwise, we can keep moving. Do we want to look at it? Do we want to draw it out? I wish there were whiteboards in here because I could have us all draw it out, but as it is, we'll move on, and if we have time at the end, we can draw it out. Okay. Is that enough? Anything else you want to talk about?
While you're talking about CD8, so like I forgot how they have their CD4 or CD cells.
Selection?
Yeah.
Let's go through selection. I would love to go through selection. Okay. I would say one of the most important things to understand for selection is that selection for B cells is different for selection than selection for T cells. So, where does selection for B cells happen? Bone marrow. Brilliant. Okay. Where does selection for T cells happen? It's going to be our thymus, which this comes up in transplant immunology, so that's a pretty good thing to remember is bone marrow is for B cells, thymus is for T cells in terms of where the selection process occurs. B cells do not undergo positive selection in the same way that T cells do. they have like a base level selection where like if they don't work at all, they're probably not going to be like released, but they don't undergo the same positive selection that T cells do. T cells undergo both positive and negative selection. Let me see where my slide is that I like. Okay. So in terms of T cell selection, the basic process is we start out. Okay, so in the bone marrow, we make our little like baby T cell, and then that gets sent up to the thymus, and then that is where the actual selection process occurs. Because no selection has occurred until we get to the thymus, we don't want that thing to have any abilities, because if it like activates on the way to the thymus, you're like, it's no good. So our T cells are like essentially completely inert until they make it to the thymus. That is when they undergo their like VDJ rearrangement process, and then they're going to express both their MHC1, or sorry, they're going to express both CD4 and CD8 TCRs. This is when they're, I think it's double positive is the term on the worksheet. That's when we know that they have both receptors, and then they will be selected for what is it? MHC restriction, I think is the term. Yeah, MHC restriction. So we start with both, then we get presented with some MHC proteins to see what these CD4 and CD8 receptors are able to bind to. They have to meet that minimum for our threshold. So we want them to be able to bind above our lower threshold, and that is positive selection. At the same time, we're undergoing MHC restriction, which means we are picking one, a CD8 or a CD4. Whichever one binds stronger is the one that we're going to pick. So if we have a T cell that has like an MHC, sorry, a CD4 TCR that binds really strongly, and then a CD8 TCR that binds weaker. We want the one that binds strongly because I want to say it would be more effective. That's not necessarily true. It's just how the system works. We pick the one that binds more strongly, and then we stick with that one. We get rid of the other one. That is when it is positive for either CD4 or CD8, negative for the other one. Not that I don't think you super need to worry about that, like double positive, single positive. It's just, I think, helpful for understanding the process. I wouldn't get too caught up in those terms. Anyway, after we've done the MHC restriction process, now we have a T cell that is either CD4 or CD8, and now we want to make sure it's not going to bind self. Binding self is important for making sure we're avoiding autoimmunity. So any cell that binds too strongly to self is going to get apoptosized. So do I have a good... Yeah. So, okay. In the thymus, because we don't have any signal 1 or any signal 2 or signal 3, if it binds above that threshold, that means that in the periphery, it would be automatically activated. Because our apoptosis threshold in the thymus is the same as our activation threshold in the periphery. So, where's my slide about? There's this concept of like binding strengths, which goes with the threshold model, where essentially like the strength of the interaction between the two cells is what determines the like signaling that activates a T cell or a B cell. So when we have this mechanical pressure that's in the middle, that indicates like it's our baseline for where we want our MHC1 and CD8 T cell TCR or MHC2 and CD4 TCR to be. We want those baseline so that when we get signals 2 and 3, that mechanical pressure is increased, our binding gets tighter, and we move up and into the activation threshold in the periphery. But if it is too high in the thymus, then that means regardless of whether we have signals 2 and 3, that cell would be activated, and that's what we want to avoid. We want to have that signal 2 and 3 be necessary for activation. So, for the process of negative selection, it's important that we get rid of those cells that would activate on their own outside of the thymus, because those are our cells that are going to cause things like autoimmunity and allergies. That is the basis of negative threshold, or negative selection. If it binds too strongly, it gets killed. We don't want it out in the periphery. I feel like that's. Let me see if we have any practice questions in here. Okay, actually, first of all, does that make sense? Do we have any questions about this? So first positive selection, and then after that, so positive selection gets rid of everything that doesn't bind, and then negative selection, and then there's like more stuff, and then negative selection gets rid of everything that does bind above above the activation threshold. That would mean that like an auto thing, and then the last part that I forgot. Okay, so but like on that same thought, there was just one other thing that I just wanted to write down. In that, I know that's super vague, but if that's missing anything, then no. Great question. To lay it out as straightforward as I can, we've got positive selection, which is getting rid of super weak binding cells. At the same time, more or less, we've got MHC restriction, which I think is what you're thinking of. MHC restriction is where we pick whether we're CD4 or CD8, and that's just based on whichever one's stronger. And then we got negative selection once we've picked one. And the negative selection is just going to apply to whichever one we've already picked. We've committed to one. If that one's too high and the other one would have been low enough, too bad. We are stuck with the one that we picked that was stronger, and that one gets negatively selected out. Okay, that's definitely, yeah. Cool. How do we feel about that? Okay. We can do a practice question if you want. I would say it's fairly likely that we're gonna get a question about like whether something might be selected positively or negatively out. There's a chance we'll encounter something like that on the exam, so we can go through one if you want. Yeah, let's do that. Okay. Oh, I will say there's no like set positive and negative limit. So people have different thresholds, which I might have a slide about. No, I don't. People have different thresholds, and that kind of determines how broad or how narrow their diversity of binding is. There's advantages and disadvantages to each. We went over this in class, and we can talk about it more if you guys want to. But essentially, my point is you will see different percentages as the markers for either threshold, depending on the individual. So let's start with somebody with, okay, actually, here's what we're gonna do. Okay, somebody give me a number. I'm gonna go with 36. Okay. Oh, shit, I need two numbers. You know what? 8 and 36 actually is great. Okay. 8 is going to be our CD8 receptor. 36 is going to be our CD4 receptor. These are our threshold numbers. Okay, walk me through this. What are we doing first? Positive selection. Brilliant. So if we've got a CD8 cell, or a CD8 TCR that binds at 8% strength, and then we've got a CD4 that binds at, what was it, 36? 36. 36%. Who's making it? Oh, actually, is this cell going to be apoptosized in positive selection? Brilliant. Which one's getting picked? Oh, I read it. Okay, so now we've got a CD4 specific T cell that binds at 36%. Sick. Do we want, are we gonna, okay, what's next? Negative selection. Are we making it out? Are we making it into the periphery? Brilliant. Okay. That should be pretty solid for what we might encounter on the exam. We can go about it in more detail if any questions. No, we feel good about this? Cool. Okay. How do we feel about transplants? Let's just go through some transplant stuff and see how we do on these questions, and then we can discuss it further. I would say it's pretty likely that she asks a transplant question that is going to try and challenge you a little bit. So I would say it's a good idea to make sure that we have a pretty solid idea of transplants and the different types of disease that or issues that we can encounter after a transplant. So okay, if we do a bone marrow transplant and we have some kind of like rejection or it doesn't go well, what kind of disease is that going to be? GVHD. Do we all know why that is? Okay, let's talk about it. Give me one second. Okay. So when we do a transplant, we have two people involved. Two sets of DNA is how I like to think about it. We've got our recipient, um, and then God, these are recipient. And then we've got our donor. Okay. Depending on what type of tissue is donated, we're going to have an immune system that matches either the donor or the recipient. So when we're looking at a transplant question, our first question is where is the immune system coming from? Okay. So we'll start with bone marrow because it's the weirder example. So our donor is where our bone marrow is from. Which means any any DNA belonging to any immune cell is going to be from our donor. To get into the technicalities of this for just a second, when we have a recipient who is getting a bone marrow transplant, we kill all of their existing immune cells. So they get a whole new set. We're starting over with what we got donated, which means any B cell, any T cell that this recipient has from the moment they get the bone marrow transplanted is going to be made from the DNA of our donor. Okay. The second question we want to ask is, where are our adaptive cells, trained? Okay. So that would be baller. Thank you so much. Okay. Hold on. There we go. Okay. So, any immune cells coming from this guy. We just went over selection, so we know that our B cells and T cells are trained in different places. Where are our B cells trained? Where are they selected? Bone marrow. So our B cells in this case are from the bone marrow. And they know the DNA, they understand the self that is shown in this bone marrow, which is going to be from our donor. Which means our B cells know our donor. They don't know our recipient. They don't recognize our recipient necessarily as self. Our T cells, they still come from the bone marrow, which means that if we're doing one of those flow analysis things where it's whose cells are these? They're still from the donor. They're still donor cells made from donor DNA. But where are they trained? Okay. If this patient is 10 years old, do they have a thymus still? Brilliant. Which means they are trained in our recipient thymus, which means that the self that they know is our recipient. So our T cells know our recipient, our B cells don't. Okay, we understand this. Actually, before we move on, if our patient is 50, do they have a thymus? Brilliant. Do they have T cells? They have pre-T cells, but they don't have anywhere for those T cells to grow up and become big, beautiful, functional T cells. So if they don't have a thymus, we don't really have T cells. We just have B cells. Okay. Well, we're going to keep working under the assumption that this is a 10-year-old. And that he has a full set of functional T cells that recognize himself. And he has B cells that recognize his donor. Okay. Then what we want to ask is, what is our MHC1 match? Okay. MHC1 we use as our litmus test for how well a match is because actually you guys tell me why. What is important about MHC1 that makes it noteworthy in terms of immune responses? Every cell every nucleated cell expresses MHC1. So if something is wrong with our ability to recognize MHC1, that affects every single cell. Additionally, MHC1 is what binds to CD8 T cells, which means it's what binds to CTLs, which are licensed to kill. So if you have an MHC1 problem and you get like an activated CD8 T cell against your MHC1, which is on every cell in the body, that's not good. So we are going to use MHC1 as our like representative for MASH, in that it's the one that's most significant if you have a mismatch. Okay, let's say it's 65%. Are we going to do the transplant? What if it's 79%? Are we going to do the transplant? Brilliant. Our transplant number, our golden number is 75%. If it's above a 75% match, we're good. Okay. So let's say we have a 76% match for our MHC1 between our donor and our recipient. We know that we have a full set of T cells that match our recipient. We know that we have B cells that match our donor, but they're still present. What are we looking at in terms of immune function? Do we have a good system? Are we happy with it? Okay. Our B cells here are still going to be created consistently for the existence of this bone marrow. This is why we are going to continue to be on immunosuppressants for the rest of our life if we're this recipient. These bone marrow T cells, these B cells know this guy's body, and for the rest of this guy's life, he's gonna have B cells in him that recognize another guy, which means at any point we could get that short-term B cell response, or you're gonna get some IgM because you're gonna get some recognition of some kind of self-epitope. It could just randomly happen at any time when we get a new B cell. That's why we're going to stay on our immunosuppressives. Is it going to be a big problem without our T cells recognizing our donor? Are we going to get we're going to get any memory against self-epitopes from this recipient? No. Brilliant. If we had some kind of issue, this would be graft versus host disease. I know we talked about this. The way to remember this is that it is the graft that is attacking the host. Because the graft here is the immune system. The immune system is what we are transplanting. The bone marrow is the actual physical thing being transplanted, but because that's the source, essentially, of our immune system, that's what we're transplanting. That's the graft. Does that make sense? Do we feel good about that? Okay. I'm going to talk real quick about like a liver transplant or like another organ transplant, just so that we're clear what the comparison is. If we have a liver being transplanted, liver. There we go. We got a liver from a donor. Where's our immune system from if we've got a donated liver? It's from our recipient. Where are the adaptive cells trained? Recipient. Brilliant. So we've got B cells and T cells that are from our recipient. and are trained in our recipient. Our MHC1 match is going to be above a 75% because otherwise they wouldn't do it. But let's say it's like the doctor like read the numbers wrong and it's like a 57% match actually. What we're going to see there is a rejection of the graft. And now I can't remember what the actual term is. It's transplant rejection, right? Transplant rejection. The reason for that is because it is the immune system of the recipient that is rejecting the graft. So transplant rejection is when it's a donated tissue that is being rejected by the recipient immune system. Does that make sense? Okay. We'll talk about a thymic transplant real quick, just as another comparison. If we have a thymic transplant, we've got an immune system from who? Who is our immune system coming from if it's just the thymus that got transferred over? It's gonna be from the recipient because the recipient is who the bone marrow comes from. So any of the cells that come from this bone marrow are gonna have the same DNA as that bone marrow, as whoever the bone marrow belongs to, which means all of the proteins and stuff are from the bone marrow, and that's what we would put on our little like flow charts. Our adaptive cells are trained though where? Our bone marrow for the B cells and our thymus for the T cells. So do our B cells know our recipient or our donor? They know our recipient still. Who do our T cells know? They know the donor. We don't even care about MHC1 match for this because it's stupid and you shouldn't do it. But hypothetically, MHC1 above 75. I just want to, that's important. Okay, in this case, what we have is autoimmunity. Because our immune system has the DNA of our recipient, but because it knows our donor, it's going to end up attacking recipient cells, which means it is recipient versus recipient. That's why it's autoimmunity. Does that make sense? Okay. I hope this doesn't feel like too much like repetition. I want it to be pretty solidly reinforced because she's probably going to ask you like a breaking the system question about transplant stuff. So it's good to really thoroughly understand the like mechanisms behind this and the ideas behind where it comes from, where it's learning, and what that means. Do we feel good about this? Do we have any questions? Okay. Is there anything else worth mentioning? She always mentions allergies in reference to this. I don't on the worksheet. It was like the 4 options were transplant rejection, GVHD, autoimmunity, and allergies. I would not necessarily, I don't think there's a way that allergies could be a consequence of a transplant. I just want to throw that out there just so that it's just something to think about in terms of like, if you need to cross an answer off. Although maybe if she breaks the system hard enough, who knows? Okay. Hold on, I had somewhere I wanted to go with this and then I blanked. How do we feel about germinal centers? Okay. Probably there's not going to be any super challenging, crazy questions on germinal centers. But let's just review that super fast while I figure out what the other thing I wanted to talk about was. Oh, I remember. Okay. Real quick, we'll do germinal centers and then we'll go back. Okay. The main premise with germinal centers is that you are forcing like a natural selection process to happen in like a we have T follicular helper cells and FDCs, right? Follicular dendritic cells? Yeah. So a follicle is like an enclosed space, like a hair follicle. It's like got a hollow space that's surrounded by stuff. The reason I emphasize that is because all of this is happening in like its own little section of your lymph node. What we're doing is we're creating like a rapid mutation by having like a mass proliferation of these B cells in that dendritic cell or in that germinal center, and then we're doing selection. We're manufacturing selection using those dendritic cells and those TH cells. Do we have any specific questions about germinal centers? That was a real brief overview. What's I'm real like? Yes. I'm gonna be less specific about this than I am about most things because I don't remember it as well. I don't think that you're gonna encounter any super specific questions on it, but let's go over the general process. Actually, something I think is important to note that is maybe a little confusing is that when we get an initial B cell activation, we get the like base cells for a germinal center for a whole like clonal expansion of those IgM effectors, and we get IgM memory. So, um, okay. We start with our B cell and our T cell, our T helper cell. And then they do their thing, and we get our B cell is activated now. We're gonna start out. Oh, I actually have a slide for this. We're gonna start out with our like base products of this, which are gonna be our memory B cell of our IgM, because that's what we have for now. So far, we just have an IgM B cell. So we're gonna start out with memory IgM. And we're gonna start out with short-lived plasma cells. So these are our IgM plasma cells. And these are going to last just the extent of this one infection. They're not going to go past that. And that's also, this is why when we have a transplant, we're not worried about any symptoms past like 2 weeks periods because we're only ever going to get these short-lived ones. Okay, we have these two, which are just from that IgM plasma or from the IgM B cell. And then we have this B cell that's gonna like start a germinal center essentially. This guy then is the beginning of our this guy forms our follicle with the help of our dendritic cell and our T follicular helper cell. So those three cell types are going to start this dendritic or this germinal center, and then this guy is going to be the like base for that rapid proliferation that somatic hypermutation, sorry. And that's how we're going to get our germinal center process. That's the root of it. Then, once we've gotten this started, we get like mass replication of this initial cell. In the process, we get lots of point mutations. So with those point mutations, we get slight differences in our VDJ. So we still have just the 3 VDJ segments that we picked when we first made this B cell. It's going to be the 3 that we originally had, but now we're getting like tiny little changes of 1 at a time in here. And we're getting lots of them. This is where it's like natural selection. We start out with a big population, and then we select for the ones that bind best to our follicular dendritic cell. The follicular dendritic cell is going to be presenting all these little chunks of pathogen, all these epitopes, and these individual clones from this B cell, the germinal center B cell, are going to either die or continue to. They're going to die or they're not going to die in this process of binding to that dendritic cell. So we get a whole lot of proliferation, and we also get a whole lot of death. And then in the process, we get either, well, once we've bound to our epitope on our follicular dendritic cell, we're also gonna interact with that the T follicular helper cell, and then from there we get the final result of long-lived plasma cells, which are going to be able to secrete plasma for a long time, which means we'll get like, say it's a viral response, we're just gonna get like a pretty steady supply of IgG that matches this epitope, whichever one the point mutations, or whichever one has the point mutations that were best selected for. And then we're going, what's on?
So basically, you should kind of like adding basic.
Oh, yeah. Point mutation is just going to be like 1 at a time. We're doing super small changes, which will build up over time, and we'll like cycle through this a few times. So the longer we run it, the more that we select for, and the better our B cells are going to be. With each batch that we go through, we're going to get those plasma cells, which are now pumping out whatever antibody we've class switched to, and we're going to get a memory cell of that B cell, of this new class switched, like, adapted B cell. In terms of the class switching, so I was talking about this with her earlier because there was a question yesterday that me and the other ULAs were confused about, which was, so she asked about T follicular helper cell function and said that there would still be class switched B cells, and we were confused about that. So I talked to her about it. From what she explained to me, the class switching process begins once this guy is made. So once this is started, we're gonna have some like baby B cells that do class switching. They're gonna do that cutting out of the antibody DNA. I think I have this somewhere. Not there. Here it is. So, this process, the cutting of any in between antibodies, is gonna start once this guy's there. She wouldn't ask you something that was as challenging as that question was, but essentially what we want to understand is that we get modifications to this DNA similar to what we did with BDJ rearrangement, so that any plasma cell that comes from whichever plasma cell comes out of the germinal center is going to be class switched, and they will all consistently produce that same antibody. Cool. That should be a pretty good. That should cover most of the germinal center stuff. How do we feel about that? Does that make sense? Excellent. Okay. I have something that oh, it's right here. That's beautiful. I want to talk about this type of problem. This is going to be really good exam practice. How do we feel about these problem types? This is something we've seen a few times. Let's go over it. Okay. With this type of question, what we want to start with, or what I would start with, is looking at the entire contents of whatever is about to get phagocytosed. Whatever the environmental thing is, contains multiple different epitopes and multiple different components here. With this one, we have a host apoptotic body with a herpes virus in it. Do we have self-epitopes that are going to be phagocytosed? Yes, we will, because we've got that host apoptotic body. Do we have PAMPs? Yes, because we are ingesting that herpes virus, the dendritic cell recognizes that there are PAMPs. Once it phagocytoses this, it's going to go through our whole processing thing with the phagocytic, the breakdown, and then it's going to present all of the epitopes onto our MHC2 proteins. Does it distinguish between what specific organism these epitopes came from when it's presenting? No. It's just going to present little chunks. It doesn't say anything about where they came from. When whatever T cell is there interacts with it, all it sees is the epitope. It doesn't get any more information than that about that specific epitope. What it does get is whatever consequences are downstream of PAMP detection, which means this dendritic cell knows that it got a PAMP, which means it's expressing B7 and it is secreting cytokines. It's expressing signals 2 and 3. That's what we want to consider when we're looking at whether any of these activations are going to happen. Do we have PAMPs? And is the epitope being presented? So, for A, we have glucose transporters that have been phagocytosed and are being presented. Do we have a glucose transporter specific T cell? Brilliant. It is a CD4 T cell. Is that CD4 T cell going to get activated? Yes. Why is it going to get activated? If the glucose transporter was presented to it, and it got signals 2 and 3 because of those PAMs. What about the cat dander? Are we going to get activation of the cat dander T cell? No. Why not? There's no cat dander to present. We don't have an allergy to cat dander because there's no cat dander on this dendritic cell. What's up? Yes, because it's a cell protein or cell protein, but it's yes. Okay, so so it is autoimmunity because it's a self epitope. I wouldn't try to connect this at all to the autoimmunity that we talked about with transplants because it's a different type of autoimmunity. But because the immune system is activated against this self protein, that's autoimmunity. What I would focus on here is the glucose transporter part because that's the key to this question, rather than understanding autoimmunity itself. Of course. Okay. How about herpes? Are we going to have an immune response or a memory T cell to herpes? Brilliant. Why? Because there's herpes presented. There's herpes epitopes, and we got PAMPs. Brilliant. Polio. Are we gonna see a polio? No. Sick. Oh, actually, reverse. Just kidding. Yes. No, sorry. We are going back. We are gonna see that autoimmunity or the response to herpes, but there's more to it than just signals 2 and 3 from the dendritic cell and the presentation by the MHC1. We also, because it's a CD8 T cell, we also have to have the second signal 2 and second signal 3. Are we getting those? Where are we getting those? It's from our T cell that is doing the autoimmunity. So, because this CD4 T cell was able to bind to that dendritic cell and become activated, it's now also capable of providing that second signal 2 and 3 to our herpes virus. Let's say we have let's say we just don't have this CD4 T cell. Are we going to get activation of our herpes virus specific CD8 T cell? No, because there is no CD4 T cell which will become activated to provide signals 2 and 3. Does that make sense? What's up?
So if we don't see all
If you don't see, if it's not like listed as something that is an environmental, like something present, yeah, assume it's not there. So like, since we don't see cat dander listed as an environmental thing, we're just assuming it's not relevant here. Does that answer your question? Cool. What's up?
So is that
We also have that autoimmunity because we activated the CD4 T cell.
Oh.
So it's A and C is dependent on A because we needed our CD4 to be activated in order to activate our CD8. What's up?
Since but the CD4 T cell that's being activated in the glucose transporter, if it goes and like gets presented and then the glucose transporter will cause like problems with other cells and glucose transporters. Like that's quite scary.
So this is actually something. This is a really good question. Us ULAs got in a long argument about this actually, and we forgot to ask Justine for the concrete answer. So I will tell you what we were thinking. It's not going to come up on the exam. So, when we were talking about the Hampton problem, the Hampton effect, which is the thing with our, what is it called? What is the antibiotic? Yes. What is the thing called? Penicillin. Thank you. Sorry, guys. Okay. When we have our penicillin bound to our bacteria, and we phagocytose it, and we get expression of both things, and we get separate activation of two penicillin and to our bacteria. What we talked about in class was that if your penicillin was, or if you had a CD4 T cell that was activated against penicillin, you wouldn't have allergies because the CD4 T cell doesn't activate the B cell, which would have the actual effect of like reacting to the penicillin. There, hypothetically, anytime you encounter penicillin in the future, your CD4 T cells would initiate some kind of response, secrete cytokines, like activate nearby cells with their cytokines, that kind of thing. However, that in and of itself isn't realistically going to do anything other than cause like minor swelling. Because you're getting like recruitment and proliferation hypothetically. Like that's sort of what we're looking at with the CD4 T cell response. I will say if you have a CD4 T cell response to penicillin, and then at some point in the future, a dendritic cell brings another, like it phagocytoses another bacteria that has penicillin bound to it, and it presents that penicillin to that CD4 T cell, which is now a TH cell. Hypothetically, you just get a faster response to that bacteria because it's already familiar with the penicillin, and will help, like, begin the response against that bacteria. Does that count as an allergy? Not in terms of what Justine is looking for with her questions. So, does that answer your question of like future responses? There could be consequences. I would argue that you would see some issues if you had that autoimmunity. But that's okay. So yeah, I actually think that she had us not select autoimmunity because of the fact that it's a CD4 T cell. I just realized that is why A was not an answer. So you do have activation. You don't technically have, by what she, by her standards of like a full response of like actual issues and an actual full reaction, you won't have autoimmunity in those terms. So sorry. You still have activation though, and that is what we care about in terms of the CD8 T cell activation and that hierarchy. And you do have a memory T cell against the glucose transporters. Okay. How do we feel about that? Is that good? Do we have any questions?
The answer is just C.
I believe in class the answer was just C. I like mildly disagree with that. But I believe on the exam the answer would just be C because it's a TH a TH cell that would be reacting to that glucose transporter. Sorry for that important clarification. Okay. It is 8:30. So I don't want to I don't think we need to go through any more of these concepts like step by step. Do we have any just like clarifying questions, anything we want to talk about? Small things, questions we don't understand? Oh, yeah, let's do that. Okay. Let's do that. Yes.
Also, just a quick question. So, y'all, I have this message. Y'all take the exams as well, like before you do?
It depends on how early she finishes them. She's gonna send me her version of the exam and I was gonna go through it tonight. Is there a reason?
Yes, sorry, because I was gonna ask, like what you thought it was, what you felt least prepared for when you took the exam, not as the TA, but like,
Yeah.
that's why, like, exam. So,
The exams are pretty similar. Like, they're really similar from semester to semester. Personally, okay. generally, I kind of struggled with the wording on the exams and some of the like specific details and like getting caught up, things like autoimmunity not being technically selected because it's a CD4 T cell. Those were the kind of details that always caught me up. Which is why I think it's a really good idea to look at the questions in the slides and make sure that you're really comfortable with the answers. It's like the one we just went over, where I totally forgot that A shouldn't have been selected. Those are good things to look out for. What's up?
There was also a CD8 T cell that had a receptor bound to the glucose transporter in that then cause autoimmunity.
Yes. Because the CD8 T cell can do what? Brilliant. Okay. So yes, I would say reviewing questions just to see what kind of like phrasing changes what is the correct answer. That's a really good strategy. I also tended to just be bad at memorizing things. That's pretty fixable. That's why I recommend looking at like that T cell slide, doing some review of your innate stuff. I really recommend looking at the prep quizzes to get some of those like key association things, some of your like vocab type stuff. It's a good way to memorize stuff. Other than that, I can't remember being super tripped up by anything. Um, what we've talked about today, I feel like is pretty solid in terms of like reviewing the overall concepts. Um, double check on some of those. If you can find them in the lectures, go back and watch her explanations for the answers to questions. If you want to be like super solid on the like wording and what specific things she's gonna like trip you up on. Does that answer your question? What's up? That's a really good question. I couldn't say. Um, I don't remember anything. I think because we're going through a lot of the older stuff, like transplants and VDJ and stuff, that's I think adaptive. Honestly, this exam is easier than exam one in terms of like everything connects a little more. So there's less like just pure memorization and like understanding of like sort of niche concepts. It's more about understanding the patterns. Um, I think if you guys did your maps and you felt pretty solid on your maps, um, and you remember transplant stuff, you remember VDJ, you're probably pretty set. If you're like me and you get tripped up by the small details, you have corrections. And I don't think that's necessarily a bad thing to remember. I don't think you need to get a 90 on your first I don't think you need to get a 90 and then not rely on corrections at all. I would say as long as you feel pretty comfortable with the concepts that we're talking about and understanding why the answer is a certain way, you're probably solid. Okay, VDJ. So, okay, actually, real quick, I'm just gonna go through the process really fast. We start out with our full DNA sequence, which is the same in every like pre-T, every like pre-B cell or whatever. And that contains all of your V's, all of your D's, all of your J's. And then we go and we pick one. I think you start with D and J. You bring them together with RAG1 and RAG2. You get that hairpin sequence. You cut it off. We add in with TDT. Yeah, of course. Good luck. With TDT and the other guy, exonuclease, we do like essentially point mutations on either end. And then we reanneal them together using our DNA ligase. That's not right. Yeah, I have to look at the slides again. This is something where you just want to do a quick check of the exact terms of the enzymes. Oh, it is ligases. Whatever. Then we're gonna do that again with our other two. So we'll still start with our D and then our V. We bring them together. We do the whole process, TDT, exonuclease. Now we have a DNA segment. Well, we have our DNA is permanently modified so that it has one V, one D, and one J. Boom. Brilliant. Any baby cell, that's not what it's called, but any cell that comes from that will have that same DNA, which means any receptor will have that same DNA. Cool. We want to focus from DNA to the mRNA and then to our actual protein. These are good practice questions. When we have our BDJ segments next to each other, we're still going to have our V's at the beginning and our J's at the end. And then we have our constant region. And this is what our DNA looks like, so we need to do a little bit more modification before we get just one V, one D, and one J. So to get rid of those V's, we start our transcription at this first V. And that's how we get rid of this. And then we end it at our constant region still. So step 1, which is just basic transcription, we still have our J's in between our wanted J and our constant region. Our extra J's. Then we do splicing, and when we do splicing, we can get rid of the little like middle J's. And that is going to give us our final transcribable or translatable mRNA. Cool. That is our process from going from full DNA with all of our V's, all of our D's, all of our J's to 1V, 1D, 1J mRNA that is able to be made into our protein. And then we get from that our protein. So I'm just going to draw ECR. And this guy has its variable regions. So our V and our D and our J are along this edge, this like surface area. That's the full process of DNA to protein. Cool. She likes these questions that are like, what went wrong? How would you guys answer this one? If we have extra V's in it. Hey, RNA polymerase didn't begin at the correct location. What's supposed to mean? I think it should be transcription. I could be wrong. Anyway, RNA polymerase didn't start at the correct point. RAG1 and RAG2 did fine because we have the correct V3, D3, and J2. RNA splicing did occur because our J's are gone. Yeah, it occurred correctly because our J's are gone. Okay. How about this one? What would you guys say? Say that again? B. Brilliant. B. Rag 1 and Rag 2. Why? Because we've got two Ds, which means one of our Ds was grabbed wrong. Brilliant. Okay. What's up?
The other game also is this example where like there's whole and she said it was already in information.
Okay. That's because what you're looking at there is the DNA. So, because that's the DNA, we haven't started transcription yet, and we haven't done the splicing. So we still have these in there because we still have our beginning and we still have our end. From there, you're gonna get your mRNA. Oh, hold on. From there, you're gonna get further modification to take out those extra codons for the antibody type. And then once that happens, that'll determine the ending. And then the splicing and stuff happens. But the DNA is still going to contain those. Brilliant. Okay. Anything else? Do we have any more questions? Anything we want to talk about?
As you were going, can you do that?
So just with like VDJ arrangement and then class switching, are these things happening at like different times or simultaneous? Like transcription and stuff like that. Because I know that that's the policy arrangement. Class switching.
With VDJ and class switching?
Yeah, I thought like once in the class to be some kind of sliced up, but they happening like at the same time.
So our VDJ is done well before we ever get to the class switching process because our VDJ happens before it even leaves the bone marrow. And our class switching happens once we form a germinal center. So we're not doing any more we don't touch VDJ outside of the bone marrow. We just are going to focus on that antibody, like class switching, because we've gained new information there. But we like what our VDJ is if we've activated our B cell. We're content with that. We're not touching it except for those point mutations in the germinal center. Yeah. Does that answer your question? Cool. What's up?
Oh. You were going through some slides. Can you go over the bars? Kind of confused. Like, you know how you have those, she already go over. Okay, no, then that's fine.
If you have a specific question, I'd love to hear it. Let's see if I talked about it already.
You just said
Oh, well, when there was one in like class, she showed two different lines, and I didn't know.
Okay, I have if you go to the
I mean, you already talked about it.
I'm just gonna
Show me. Yeah.
how can I get the Canvas clip? Okay, hold on. In the on Canvas, I have laid out instructions for how to do it step by step in that Q&A sheet. I typed it all out. That should walk you through it. This is recorded also, and I'm going to post it so you can watch that too. Cool. Okay. Anything else?
Keeping question.
Yes.
Sorry, worksheets tomorrow. The back of the worksheet that we did the germinal centers on.
That's not the one you turn in. You'll do the timeline that you got today. That's the old version that I adapted. So you can try it if you want to challenge, but that's not the one to turn in first. Have a good night, guys. Anything else? Do we feel decent? Cool.
Yes, this one. So anything that's wrong with the main section is my on proof. It's gonna be where I want to do. Well, yeah. I would say that's mostly true. Except she'll show you. Okay, she'll show you with those little stars which one feed D and J or sorry, which one rag 1 and rag 2 are supposed to bind to. Hypothetically, if you had like V2 here, it's also rag 1 and rag 2's fault. Since they picked the wrong one. For the most part, if there's extra V's in front of the correct V or extra J's after the correct J, then yes, that's gonna be RNA preliminary results. Okay. Unless anybody has any other questions, I'm gonna call it there. Cool. No.